Hey everyone, think about it for a second. Like all the stuff your computer's juggling at any given time, right? You're writing an email, got a spreadsheet open in the background, maybe even a game running, and it all feels so smooth.
Yeah, it really does.
But have you ever stopped and thought about how your computer manages to pull off that multitasking magic?
It's a great question, and it's something that's fundamental to how we use computers today. In this deep dive, we're going to try to unpack the different ways computers tackle multiple tasks, seemingly at the same time. We've got some great research to look at today.
Yeah.
And hopefully we'll be able to give you a better idea of what's actually happening under the hood and why some processes feel so much faster than others.
It's like peeking behind the curtain, right?
Yeah, exactly.
Like looking at the engine that's running your entire digital life.
Absolutely.
Our sources talk about three main techniques: sequential, parallel, and distributed computing. And that's what we're going to explore today, kind of weigh their pros and cons, see when each one makes the most sense.
Sounds good.
So let's start with the most basic one, sequential computing.
Yeah, and the source actually uses this great analogy for sequential computing.
Right.
It's like a factory assembly line. Each task has to go through the line one after the other. Task A is completed, then it moves on down the line, task B starts, and so on. There's a very specific order, and no two tasks can happen at the same time.
I see. So it's really like a one-track process, right?
Exactly.
And the source mentions that this is very often related to the hardware itself. Typically, sequential computing happens on a single processing core within your computer's CPU, which is kind of like having only one worker on that entire assembly line, right?
Yeah, precisely.
And I know we live in this world where multitasking is everything and speed is everything, but sequential computing is still really important, right?
Yeah, because as the source points out, sometimes there are these dependencies between tasks. Sometimes a task needs information or output from the previous task before it can even begin. So task B literally can't start until task A is finished and has delivered something, right?
Exactly. It's, you can't frost a cake until it's been baked.
Exactly. Perfect analogy.
Yeah.
And the source actually gives us an example of the timing involved. Let's say task A takes 50 milliseconds, task B takes 40 milliseconds, and task C takes 35 milliseconds.
Okay.
If they have to run sequentially, one after the other, the total time is you just add them up.
Right.
125 milliseconds, just one thing happening at a time.
Exactly. Now, let's move on to something a little more complex. Let's talk about parallel computing.
Okay, now we're getting to the fun stuff.
Yeah.
So what's the basic idea behind parallel computing?
So imagine taking a program, a big task, and breaking it down into these smaller sequential chunks. But the difference here is that these chunks can be scheduled to run at the same time, usually all on the same computer.
I see.
The source emphasizes that there might still be sequential parts even within parallel computing, but the main goal is to do as much as possible at the same time.
Okay, so instead of one worker on that assembly line, now you've got a whole team of workers.
Exactly.
And they can each work on different parts of the product at the same time.
That's a great way to think about it. And the source really highlights how this connects to modern computer hardware. We have CPUs today with multiple cores. It mentions 64 plus cores. I mean, just think about how many apps and processes your phone or laptop's running at the same time. Having all those cores means the system can dedicate processing power to each task, making everything feel faster, smoother, like having a whole room full of workers, all tackling different parts of the job.
Wow, 64 plus workers. I mean, that's some serious parallel processing power. It must really speed things up.
It does, and the source actually uses this really easy to understand analogy. Think about grading papers in a classroom.
Right.
Instead of one teacher grading every single paper one by one, you could have multiple teachers each grading a portion of the stack concurrently.
Yeah, I wish my teachers had done that when I was in school.
Yeah, right.
So what are the big wins with parallel computing?
Well, the source points out several benefits. Faster operations are, obviously a big one. And it allows you to process way more data in a shorter amount of time. It's also incredibly important for things like video games, where you have tons of calculations for graphics, AI, physics, all happening in real time. And parallel systems also tend to scale better than sequential ones. You can just add more processing power, more cores, and you'll see a noticeable improvement in performance.
Okay, that makes sense. Now, give me an example. How does the timing work with parallel computing?
Okay, so let's say you've got Core 1 handling Task A, which takes 45 milliseconds, and at the same time, Core 2 is handling Task B, which takes 50 milliseconds. Core 3 jumps in and tackles task C, which takes 25 milliseconds, and then right after that, it starts on task D, which takes 30 milliseconds. So a total of 55 milliseconds on that third core.
Yeah, keep going.
Meanwhile, you've got task E running on another core, let's say, and that takes 40 milliseconds. Now here's a key thing. The total time to finish all those tasks in parallel is actually determined by the longest running core, which in this case is that 55 milliseconds on core 3. Even if other tasks finish much quicker, we have to wait for that last one to wrap up.
So it's almost like even though some parts of the job finish faster, the entire operation is held back by the slowest worker, so to speak.
Exactly. Now remember that sequential example we talked about, where tasks A, B, and C took a total of 125 milliseconds.
Right.
If we could run those same tasks in parallel, let's say A on core 1 taking 50 milliseconds, and then D and C together on core 2 taking a combined 75 milliseconds, the total parallel time would only be 75 milliseconds.
So 75 milliseconds versus 125.
Yeah.
That's a big improvement.
Huge improvement.
So the speed up time, like the source calls it, that's basically just comparing how much faster parallel is compared to sequential. Right?
Exactly. So in our example, it would be 155 divided by 75, which is like 1.67.
Right.
So in this case, using parallel processing made it almost twice as fast. It's kind of like adding more lanes to a highway. It sounds like it should just double the speed, but, if there's still a single bottleneck somewhere, everyone gets stuck.
Right. Makes sense. Okay, so parallel computing seems like a really powerful tool, but it's not a magic solution to make everything infinitely faster. Are there other downsides? Other things to watch out for?
Yeah, so the source really stresses this one limitation. The efficiency gains you get from parallel computing are still limited by the parts of the program that can't be parallelized, those sequential parts we talked about. Not every task can be broken down and run simultaneously. Some just inherently need to happen in order.
Right, like some things just have to be done step by step. You can't build a bookshelf until all the pieces have been made, right?
Exactly. So this means that at some point, just throwing more and more parallel processing power at a problem might not give you those same big speed increases. Like the source says, eventually adding parallel portions will no longer significantly increase efficiency. You're not going to get that same bang for your buck after a certain point.
I see. So there's a limit to how much you can squeeze out of that approach.
Right.
Okay, so we've gone from one worker to a whole team on the same site. Now, what about distributed computing? How is that different?
So distributed computing takes this idea of teamwork to a whole other level. Instead of just using multiple cores on one computer, it uses a network to bring in multiple physical computers to work on the same task. It's like making a broadband call, as the source puts it, reaching out across the network to get other machines involved.
So now it's not just a team in one building. It's like multiple offices or even entire factories all working together on the same project, right?
Precisely. And the source gives some really interesting examples. Things like Google Web Search and Beowulf clusters. These are huge tasks that are handled by massive numbers of interconnected computers.
So the key difference from parallel computing is that we're now talking about physically separate machines connected through a network, not just multiple cores inside one machine.
Exactly. And because it relies on a network to make all these computers talk to each other, distributed computing often involves a mix of sequential and parallel processing. Each individual computer might be doing things in order or in parallel, but they're communicating with each other over the network as part of a bigger effort.
So would it be fair to say that distributed computing could potentially be even more powerful than parallel? Like, more computers working together should equal faster results, right?
Not necessarily always faster, and this is where the source brings up a potential downside. Since distributed computing depends on the network to function, it can sometimes actually take longer than you'd think. Imagine if the network goes down, or if there's just so much data traffic that everything slows to a crawl. It's like everyone trying to get on the highway at rush hour.
So the communication itself becomes a bottleneck.
Exactly. So yeah, distributed computing has the potential for a lot of power because it uses the resources of many machines, but you also have to think about the overhead from network communication. Things like latency and reliability can become a real problem. It's not always a surefire way to get faster processing than a well-optimized parallel system on a single powerful machine.
It's not just about how many computers you have. It's about how well they can communicate with each other. Okay, so we've talked about the three main computing techniques. Let's look at some of those examples the source provides to really get this down.
Sounds good. So the first example talks about a computer with two identical processors that can run tasks in parallel. We have three processes, X, Y, and Z, and they take 50 milliseconds, 40 milliseconds, and 40 milliseconds to execute, respectively. The question is, what's the absolute shortest time it takes to execute all three? What do you think?
Okay, let me see. Two processors, three tasks. Well, process X is the longest, taking 50 milliseconds, and it will need to run on one of the processors. Now, the other processor is free to handle both Y and Z, since they only take 40 milliseconds each, so they can run at the same time on the second processor and finish within that 50 millisecond time frame that X needs. So I would say the shortest execution time is 50 milliseconds.
You got it. That's exactly what the source says. Now, on to the second example. This one asks about the time difference between running two processors in parallel versus in sequence for two tasks, A and B, which take 25 milliseconds and 45 milliseconds to execute, respectively.
Okay, so if they run one after the other sequentially, then the total time is simply the sum of their individual time. Yeah. 25 plus 45, which is 70 milliseconds. Now, if we run them in parallel, each processor can work on one task at the same time. The total time will be determined by the longer task, which is B, at 45 milliseconds. So the difference in execution time is 70 milliseconds minus 45 milliseconds, which gives us a difference of 25 milliseconds.
Exactly. You nailed that one too. Now for the third example, imagine a computer with two processors that needs to run four processes. The goal is to arrange these processes in a way that takes the least amount of time.
Okay.
The source suggests assigning processes A and B to one processor, taking 50 milliseconds total, and processes C and D to the other processor, also taking 50 milliseconds. What does this tell us about parallel processing?
It shows that it's really important to balance the workload when you're using parallel processing. By grouping tasks strategically and assigning them to the processors so they finish around the same time, you can prevent one processor from being idle while the other one is working. This balanced distribution leads to that optimal execution time of 50 milliseconds in this case.
Right on. So let's take a moment to sum up what we've learned.
Yeah, good idea.
Computers are constantly doing a ton of things, from running the operating system to all the different apps we use. They use these different computing models to handle all these tasks. Sequential computing is a basic one, where tasks are done one at a time, often because they depend on each other. Parallel computing utilizes multiple cores on a single computer to do things simultaneously, making things much faster, but it's still limited by the parts of a program that can only be run sequentially. And then we have distributed computing, which brings in a whole network of computers to tackle really big tasks. This has the potential for a lot of power, but can be hindered by network issues. It's important to remember that even within parallel computing, there are often still parts that need to be done step by step.
Yeah, so it's not just about having more powerful hardware. It's about understanding how to break down tasks, considering the relationships between them and thinking about the costs of communication. All of that plays a role in how well a computer can handle everything we ask it to do.
Absolutely. And with that in mind, here's something for you to ponder. As we become more and more reliant on AI, machine learning, and big data, which all require a ton of computing power, what do you think will be the biggest hurdles in designing future computing systems that are not just powerful but also energy efficient and can handle even more tasks as technology advances? What kind of new ideas or ways of thinking about computation might be needed to overcome these challenges?
That's definitely something to think about. It's clear that the way we compute is going to keep evolving as our needs and demands change.
For sure. It'll be interesting to see what the future holds for computing.